Okay, so I'm going to go over day 57 and give you some tips and help you get through day 57's questions. So, question number 1 says the customer care manager at a cell phone company keeps track of how long each helpline caller spends on hold before speaking to a customer service representative. He finds that the distribution of wait times for all callers has a mean of 12 minutes with a standard deviation of 5. This distribution is moderately skewed to the right. Suppose the manager takes a random sample of 10 callers and calculates the mean wait time. So what is the mean of the sampling? It says distribution of X bar. So the mean of the sampling distribution should always equal or be approximately the same as the mean of the population. So if the mean of the population is 12 minutes, then we also want X bar, the mean of the sampling distribution, to be 12 minutes. Now, is it possible to calculate the standard deviation of X bar? If it is normally distributed, or if we have a sample that is bigger than 30, we can calculate the standard deviation. But because it tells us that it is skewed to the right, so it's not normally distributed, and our sample size is not 30 or more, we're actually not going to be able to do that formula. If we were able to do it, I'm going to show you on the formula sheet for sampling distributions. It is sigma, which is the standard deviation of the population, over the square root of n. So if we were able to do it, it would be 5 over the square root of 10. But since it is skewed to the right and we have such a small sample, it's actually not possible to calculate. C, do we know the approximate shape of the sampling distribution? Again, if our random sample is at least 30, then it doesn't matter what the population is. We would say our sampling distribution is approximately normal. But since our sample is not at least 30 and the population is skewed to the right, then our sampling distribution is also going to have to be skewed to the right. So you need to explain that in C. All right, number 2. The weights of Granny Smith apples from a large orchard are normally distributed with a mean of 380 and standard deviation of 28. What is the probability that it weighs more than 400? So we want to do a normal CDF here from 400 to infinity with a mean of 380 and standard deviation of 28. And make sure that you are writing down all of that to show your work, that you don't just have a naked answer there. In B, it says 3 apples are selected from the orchard. So what's going to change is the standard deviation. It's going to be, we're going to use our formula, it's going to be 28 over the square root of 3. So our new standard deviation, if we go into Desmos, I can pull that up. Our new standard deviation for B is going to be, instead of 28, it's going to be 28 over the square root of 3. So it's going to be 16.17 would be our new standard deviation. So now we can do a normal CDF. We would go from 400 to infinity with a mean of 380, but our standard deviation is now 16.17. So to explain why the probabilities in A and B are not equal, you need to think in A, we're just talking about one single apple being more than 400 grams. And think about it, for one apple, it's more likely to happen than if they're all 3 apples. The average of all 3 of them is more than 400 grams. And again, that comes from our formula for the standard deviation. So you can show that work there in order to see that because the standard deviation is smaller, it's going to be a lot harder for it to be more than 400 grams. Okay, we're going to move to page 3. Suppose that 35% of all business executives are willing to switch companies if offered a higher salary. If a headhunter randomly contacts a simple random sample of 100 executives, what's the probability that over 40% will want to switch companies if offered a higher salary? So again, here we're wanting to see if we're talking about 100. So think about this. In this case, the mean of this is 0.35, right? So that's your P, because we're talking about proportions. So P is 0.35. So P is 0.35. And then we have 100 executives. So we need to go to our formula, okay, for proportions. And that's right here. The mean of our sampling distribution should be equal to P. So our mean is still going to be 0.35, okay? But our standard deviation is going to be this. So to find the standard deviation, we're going to do the square root of 0.35 times 1 minus 0.35 divided by n. So that would be the square root of 0.35 times 0.65 divided by 100, right? So our standard deviation now is 0.0477 if we round to 4 decimal places for proportions. 0.0477 would be our standard deviation. So we want to know the probability that over 40%. So we want to do a normal CDF from 0.40, that would be 40%, to 999 with a mean of 0.35 and a standard deviation of 0.0477. So you need to show how we got that standard deviation and then show the normal CDF formula. Okay, number 2, we're back to talking about means instead of proportions. And number 2, the average outstanding bill for delinquent customer accounts is $187.50. That's your mean, with a standard deviation of 5450. If a delinquent account is randomly chosen, what is the probability that it's over 200? So again, normal CDF, over 200 would be from 200 to 999. The mean is 187.5, and the standard deviation is 54.5. Number 3, the same problem, but now we're talking about a simple random sample of 50 accounts. What is the probability that the mean is over 200? So in this case, what we want to do is we will have a new standard deviation. So the standard deviation is no longer 54.5 because we're talking about 50 accounts. The new standard deviation is 54.5 divided by the square root of 50. So that's why that formula sheet is going to be so important. So the new standard deviation is 54.5 divided by the square root of 50. So we get a standard deviation of 7.71 or 7.707. That's our new standard deviation there. So now we can do normal CDF from 200 to 999 with a mean of 187.5 and a standard deviation now of 7.707. Number 4, the average, so we get to our last 2 here. Number 4 says the average number of daily emergency room admissions at a hospital is 85. That's your mean, with a standard deviation of 37. In an SRS of 30 days, what's the probability that is between 75 and 95? So the key is to do 37 divided by the square root of 30 to get your standard deviation. So 37 over the square root of 30 gives you 6.755. That is your new standard deviation. So we want to do a normal CDF from 75 to 95 with a mean of 85 and a standard deviation of 6.755. And then number 5, 58% of all gold dealers believe next year will be a good one to speculate. So that is the P, that is the proportion, 0.58. And an SRS of 150 was a probability that it will be between 0.55 and 0.60. So we know the lower for normal CDF is going to be 0.55. We know the upper is going to be 0.60. We know the mean is going to be 0.58. We need to find the standard deviation. So we go back to proportions. We look at our standard deviation formula. It is P is the square root of P times 1 minus P over N. So that is the square root of 0.58 times 1 minus 0.58 over and n is 150. So that gives us a standard deviation of 0.0403. So very small standard deviation there, 0.0403. So now we can go and do normal CDF from 0.55 to 0.60 with a mean of 0.58 and a standard deviation of 0.0403. Okay, so hopefully that's helped you. Remember, if we're talking about more than one thing, then that's when we use our standard deviation formula for a sampling distribution when we have more than one sample. And if we're talking about the mean, we use this formula down here, sigma over the square root of n. And if we're talking about proportions or percentages, we use this formula right here, the square root of p times 1 minus p over n. And you'll get familiar with those formulas because they will be used in the later chapters as well. All right, thanks and have a great day.